Okay, then we start with today's topic, multigrid. And what I'm going through now is sort of this multigrid part 1, 2, and 3, the appendix that you have been given in the material. So it's handwritten notes from Årset based on this nice little tutorial by Briggs, cute little book. So this is what we are going into today, starting with the basis of the classical iterative methods, and then how we could use that to construct a multigrid method. Some of this material will be too detailed, a little touching into the numerical theory behind the error, how efficient is this method. It's a little too heavy, and I would say we don't really need all the details there, but it's here, so you can play around with it if you like. We have a couple of examples, some model problems, and in the appendix actually you find the source code in Fortran and even in Pascal. None of you have ever touched Pascal, I guess. Very old language. Nobody uses it anymore. So, but we'll have a look into how such a codes can be derived. Also, we will have some MATLAB demonstrations. Funny enough, the birth of multigrid was in Russia in the early 60s by Fedorenko. He wrote an article that nobody understood until 10 years after. The Russians were extremely good numerical people in those days. They had very weak computers, so they had to make efficient algorithms. So they were very clever, but nobody else can understand it. So Fedorenko wrote some articles how to solve elliptic equations, and then a guy from Israel, I think, Archie Brandt, he sort of translated this one into a more practical approach 10 years after, and that's where the multigrid method was born. And since then it has just exploded. So nowadays everybody uses multigrid or know what multigrid is. So we have talked about this roughly already. The basic idea is to use the classical old-fashioned iterative methods, Jacobi, Gauss-Seidel, but we use them only where they are efficient, meaning removing high-frequent components of the error, not the low-frequent. There they are terrible. So we start on the fine mesh and do some iterations. Here in the text they talk about sweeps. So one sweep meaning one iteration, one calculation, one update of all your unknowns on one grid level. That's one sweep. So just exchange it with one iteration. That's a sweep. Or even also later we're going to call it one relaxation. But it still means one iteration. But we now are looking for what's called a good smoothing properties. We need a method that is very efficient by filtering out the high frequent noise, which we know, we have seen already, Jacobi, Gauss-Seidel, they are actually quite good at that. Then, after some iterations on the fine mesh, you move your then numerical approximation, your solution, onto a coarser mesh. There, your low-frequent modes of the error will now appear more high-frequent. And then we do some iterations here, or even we might solve the equation system on the coarse mesh. I mean, in 3 dimensions, a coarse mesh, if you take only every second point, you are down to 1 divided by 8 in numerical complexity, in the volume of how many unknowns you have. So the problem will be much smaller. So finding the solution here, we have to go back then to the fine mesh, which is where we want the solution in the end. And now we have to correct whatever solution we had there by the information we get from the coarse mesh. And then we might have to do this several times, flipping between those two meshes. So as it says here, the main part of these notes, based from a Multigrid tutorial by Briggs, which you have been given on the homepage. And you find a lot of material if you're interested, but I warn you, some of these books will be very heavy when it comes to numerical theory. So be my guest, but they will be tough. So we start. We have, this is also important. Remember, we start with an elliptical equation. Elliptic equation. It's the elliptical equations that are expensive to solve. Parabolic, hyperbolic, no problem. There you can march the solution forward in time. If you write them explicitly, they are very simple. Implicit methods, a little bit more tricky. You have to solve an equation system. But elliptical equations, they are the pain. Like Poisson equation, we had this one, for instance, on a domain, and if you can recall from elliptic equations, to solve it on a domain, you are going to need boundary conditions all around the boundary. You can't leave part of the boundary open. Here you don't have any real characteristics. So looking at the solution somewhere inside here, it depends on the entire boundary. If you change one value on the boundary, the entire field inside feel that one sort of instantly. So of course this is hard to solve. Everybody is talking to each other, you might say. So they are expensive. So say we want this one now to be with a central scheme, central differencing scheme. Okay, then you would write something like phi I plus 1 j 2 times phi I j plus phi I minus 1 j divided by delta x square. And then the same in the y directions equals this function f. So there you have now your stencil. And yes, you can write this one now in a matrix form. You take this one over here. Then you will have your coefficient matrix. What will it be? It will be minus 2 on the diagonal. Minus 2. And then you need one neighbor on each side. 1 and 1. Like this. And the rest of this matrix is going to be 0. Multiply now with all your unknown phis. Phi 1, 1, phi 1, 2, whatever, all the way down to phi n m equals, and here on the right hand side, if you do it very easy, f is constant, then you can write it as simple as f multiplied with delta x square. If you want to take the boundary conditions into account, say for the first one, for instance, this one, or actually this one, he will go outside the matrix. So of course he must then be known, then he will turn up here. So then here maybe you have some f, no sorry, not f, phi of 0, 1 or something like that as a boundary value, and here maybe phi n m or something like that. They will be known. If you want to have a Neumann condition, then derivative equal to 0, then some of these coefficients in first and this last point might be somewhat different. Anyhow, to obtain such a coefficient matrix, It's born from the discrete version of your partial differential equation. So this one we call large A. And this one, that is the unknown that we want. We call this one small u. And the right-hand side, which is known, of course, we just call it some f. And as a notation, he uses a wave under his symbols to mark this is a matrix, vector, and a vector. So that is the problem. Now solve this equation system. Of course, for this example, I got a 3-diagonal matrix. You can solve that easily. Thomas algorithm, straightforward, not a problem. If you are in 2 dimensions, that's a different problem. Still possible to solve it with direct method if the problem is small. The trick is when you have a whole bunch of unknowns. Say you have 1 million unknowns here. 1 million. That's a fairly big problem. 1 million unknowns. And then construct an A matrix. How big will the A matrix be? It's going to be 1 million by 1 million. Thank you very much for memory. It's going to blow any computer, of course. It's not possible. Direct methods, they will require the use of a full matrix. Most of this, the coefficient matrix alone, most of them will going to be 0. So of course you don't store it. You don't need to. You know the coefficient values. But if you want to solve it, meaning you have to find this A wave inverse, that's a full matrix. And that is then going to blow your memory. Meaning for big problems, direct methods is not available. You can't do it. Hence, we are now talking a solution using iterative methods. So then you will never set up this A matrix in practice. To find it, well, that's what we need when we are dealing with multigrid. So here, the small u, that is now the perfect solution, numerical solution to my equation system, if you can find it. And in practice, of course, we can't. We will have a numerical approximation for u, which then we call v. So v, that is the actual solution, the practical solution that we'll have available with numbers. And hopefully he will be then close to u, but that is at least the aim. Here, as also a notation, we are going to deal with different meshes, different grid systems, fine mesh, coarser mesh. We use a big omega to sort of indicate what mesh we are on. And the finest mesh, then we write omega with a superscript h here. So this is the finest mesh. For then the coarser mesh now, you will write omega 2h. You take only every second point, or say you take 2 cells and you merge them to 1. In 2 dimensions, it will be 4 cells merging to 1 coarse cell. 3D, it will be 8, and so on. Typically, you will use the doubling of meshes when you talk about coarser and coarser mesh. You don't have to. You could have actually done anything, taking 3 cells and join them to 1 big one. But people have found out that just doubling is quite efficient and very practical. The adder, that will now be the difference between the exact numerical solution u minus our numerical approximation. Then we are going to talk about norms. You have an adder, but that adder is a big vector, 1 for each of your unknowns. So you have to sort of have a number for what's the overall adder. So then we are talking about two different norms. You have the infinity norm, the first one. You just pick the biggest one, absolute value. The tour norm, that's widely used. You add the square of all the errors, and then finally take the square root of that summation and call that one R2 norm. Some people also would say take the average there. So then you multiply this one with 1 over n in front. That's your choice. You just have to be precise what you're choosing to do. But we will use these two in this text. So now when we want a solution, we obtain an approximative solution V. Now insert that one into the equation, and if it's fulfilled, the right-hand side minus the f minus a times v should then be 0. But of course it's not going to be. So here you have what's called the residual. And now the residual will be, in a sense, an error. Your equation system is not fulfilled. Then we are searching for what's called an residual equation. So we have 0 residual, then if the error, all the errors are 0, of course. But, well, we can really not find it on a computer, but we can get fairly close within machine accuracy. Yeah, we can take that already now. Why should you solve the equation system down to machine accuracy? So the solution for this equation system here, AU equals F. If you have the perfect solution, then we don't have U here, we have V. So yes, it's possible to find him fairly decent within machine accuracy, but why should you? What does the equation system say? Well, you have the double derivative equal to a right-hand side, and then the error, the higher order terms will be of order delta x square. So initially, before you even begin, you have an error given by the order of your numerical scheme. So why waste money finding him or finding the V so close to U that it is pretty much perfect, or at least machine accuracy, when you know you're going to have an error in your solution anyway? So I would say if you have an error to an order of 10% of this one, then stop. Then you don't need to work anymore. Then you don't need to continue. You have a solution which is within the error of your numerical scheme anyway. So keep that one in mind. Because when we are now going to continue here, finding the solution, we are going to play around with finding the V so close to this perfect mathematical solution U that we can hardly tell the difference on a computer between these two. But it is a waste of CPU actually to go that far. You'll see that later. The residual, the R, that can be a little bit tricky, a little dangerous to use that one as an indicator. How close are we now to a solution? Because the R, that was defined as AV minus F, no, the other way around. When you had V, so you had minus and plus equal to the residual. This is just an equation system. You can multiply this equation with 1 million. Then the residual will be 1 million times larger. So you can't really tell when he is small what does that mean. You can't really say it. So the anode, that's a more better, it's a better indicator how close you are to a solution than just the residual. Okay, the residual equation, how to achieve it? Well, you can rearrange your initial equation a little bit using now the residual, and the step from this line here to this one, that requires some attention. How can you do that? You have AU minus AV, and then you say that's the same as putting A minus V inside my coefficient matrix A. Yes, you can do that if and only if your equation system is linear. If it's a nonlinear equation system, that is not allowed. So we have something that we must keep in mind here. The residual equation possible to get only if you have a linear equation system, only if the coefficient matrix A is linear, and normally it will be. Of course, if you start with some numerical scheme, square root of something, power of 3, whatever, then it's not linear anymore. But most problems, they will be linear. Most numerical schemes will be linear. So normally not a problem. But still, it is an assumption. So keep that one in mind. And in multigrid, it is actually this residual equation we are now going to focus on. And the reason is actually quite simple. On the fine mesh, of course, you will operate with real quantities. You have a solution for your unknown. So you want this one with dimension, you might say. But on the coarser level, we are going to deal with the residual equation. And the reason is that on a coarse mesh system, we have to transfer whatever we have as the unknowns down to the coarse mesh. They will turn up into the residual. So first you start calculating the residual on the fine mesh. Then it is the residual you push down as a new right-hand side of your equation system on the coarse mesh. And then we are trying to find the anode on the coarse mesh. And then it is very nice, because there you need now an initial value. What should we start with as an anode? Of course, we start with 0. So it's much better to use the residual equation on the coarse mesh system than the sort of a coarse version of the original equation. So that is why this residual equation is important. So now, if we have the original approximation on the fine mesh, we have pushed the problem down on the coarse mesh, finding a value for the anode there, and then come back to the fine mesh again. Then we can adjust our numerical approximation so far by the anode, and hopefully then get a new value closer to the correct solution U. So that is sort of the basic idea here. Residual correction method. As examples, he has chosen here 2 different model problems. So you recognize the scheme there as double derivative equal to 0. Oh, sorry, equal to 1. No, actually equal to -1. If you take just the 1D version of this one, linear, and say my f, the right-hand side of the equation, equal to -1, you will get the top equation. What is this one-dimensional equation? If you think in terms of fluid mechanics, double derivative, say of y equals -1. That should be a Poisson solution for you. Flow between two parallel plates, and you have a constant pressure gradient, then you should obtain this Poisson parabola for the velocity profile. Later we are going to use the same equation, but then in 2 dimension, sort of the flow in a square duct. So you have a double derivative in both the x and y direction. Also, we are going to look at an equation system where we say the right-hand side is 0. Then we are searching for, say, a dummy solution. Then we know the solution is 0, and the reason to do that is any difference from 0 is an error. So that's quite convenient when you want to investigate how does the error change. But you'll see that later on. Now, set up a numerical scheme based on this equation system. Well, you can do it very crudely from this equation up here. You isolate the center point, uj, put that one on one side and throw everything else on the other side. Then you will end up with an equation such as this. So here you have sort of the recipe you can program. And if you do it like that, then we call it actually a Gauss-Seidel iteration. Because here, if you do now a for loop over all points j, you see you will update some of the values inside your unknown, inside the vector v. So one of these on the right-hand side will be from the previous iteration. The other one will be actually freshly updated. The Jacobi, he demands only old values on the right-hand side. So hence n and n for these two guys here. Then you have to use some special temporary storage or something. So that's Jacobi. Jacobi is much simple to analyze. Gauss-Seidel is a little bit more messy when some of them are freshly updated. But we will have a peek into them here. And the way you can differ between then Jacobi and Gauss-Seidel, you split your coefficient matrix into the diagonal and then the lower and upper triangle of the matrix. So here you have the diagonal. That's the D matrix then. And this triangle here, now the lower, and this one is the upper part of the matrix. So that's one way to split it up. So with Jacobi then you will have the lower and upper directly, not a problem there. But with Gauss-Seidel it will be a little bit different. Then we are talking weighted Jacobi. That's the same philosophy as we have used before with the modified Newton-Raphson. With SOR, we introduce an omega, use the same symbol here, to actually speed up the iteration process. That was the concept initially. But here we use it as a weight, and we are going here to use omega smaller than 1. And that's quite allowed. If you insert omega equals 1, okay, then you are back to the original Jacobi. So the weighted Jacobi, we will use an omega. Yeah, and that's Jacobi. No overwrite of your unknown. You have to calculate everything based on the previous values. So you need additional storage here. If you don't do it, then we call Gauss-Seidel. You don't use additional storage. We use Gauss-Seidel. So then we have to rewrite this one a little bit. But which one you use, that's your choice actually. They are more or less identical. If you want to find the solution, it turns out that Gauss-Seidel is actually a little bit faster than Jacobi, but there's not much difference between those two. So now to do some analysis, we say our equation system has been down to the trivial equation system. We put 0 on the right-hand side for simplicity. So now the solution is given before we begin. We know the solution is 0. That's sort of the dummy solution. But then we start with an initial guess, which can be whatever we want. And we know whatever is different from 0 is an adder. So it's a very nice way to do the analysis here. So now the equation system, getting very childish actually in one dimension, is this one. And so if you want to program it, you will see uj equals 1/2 of the sum of the neighbors. Should be the midpoint all the time. But of course then you have to iterate to do it many, many times. And now we start creating the initial field. We play around with it. And we are then talking about different Fourier modes. We are talking about high frequent, medium frequent, low frequent arrows that we sort of start with. And then we can follow the different arrows and see how they behave during the iteration process. So that's the idea. So here now we say k will now be a wave number. So n being the total number of points that you have. Of course, it's then limited how many waves, how many sine waves can you graphically draw with only n points. So it will be limited with the highest frequency here, of course. So k equals 1. You will have 1/2 sine wave of the entire domain, and here k3 or k6, and so you can continue. The higher k, the higher frequency. Now for every iteration, hopefully the arrow should be smaller. And now it's a question what frequency, or how will the frequency influence the reduction of the arrow? So that is quite okay to have a look at. Here you have it. The arrow versus the number of iterations. And it's not that many points here, but you see definitely what's going on. If you have low frequent arrow initially, k equals 1, you see the arrow has hardly dropped at all. But the higher the frequency, the quicker the arrow is going to drop. So I think A, B, and C. The first one was Jacobi, omega 2/3, smaller than 1. Part B, that was Gauss-Seidel with the same omega. And the last one, that's called red-black Gauss-Seidel iteration. You take first the even points, and then afterwards you take the odd points. So you split up your for loop into 2. So not that much difference, but actually he reduces the K6 faster than the 2 other ones, but not that much difference actually. Also Gauss-Seidel here, a little bit better than Jacobi. The arrow drops faster. Not much, but a little bit. If you do a log-log, you will see, no sorry, just the arrow is log. You'll get straight lines here. So of course, here is easy to see the first arrow, K1, you're going to do thousands of iterations before that anode is reduced to any significant level. But K6, he drops fairly fast. If you now do the combination, you create an anode where you superpolate the three different anode that we had: K1, K3, and K6. So we started here initially with an anode something like this. 1/3 of the sum of these three signs. Well, actually here is K1, K6, and K32. Then you see what happens. Just during the first couple of iterations, the anode drops very much, almost halved. That is the high frequent mode that now has been filtered out or removed. But the low frequent anode, staying on forever, pretty much. So the method is very efficient initially, but then you can forget it. So that's sort of the philosophy then behind Multigrid. Now, it's possible here to have a peek into why he operates like this, looking at the spectral radius of the coefficient matrix. Again, I would say this is not something that we are going to need. You can have a look at it if you're interested, finding what's called here a convergence factor and yada yada yada. So it's possible actually to get numbers for how efficient this iterative scheme are, how this convergence factor is changing during the iterative algorithm and so on, but we frankly don't really need it. Also, it's fair or easy enough with the Jacobi method. Yes, then you can find these eigenvalues sort of straightforward. With the Gauss-Seidel, you'll have a mix between new and old values. Then the analysis is going to be fairly nasty. So not so easy to do. So you can have a look at this if you want. Finding the eigenvalues, spectral radius for the coefficient matrix, yes, possible. But I would say for us, no, we don't really need it. Now, as an example, how can you represent different modes here with only 12 points? K equals 1. That's a fairly good representation of a half a sine wave. And a full one, K2, K3, K4, K6. It's starting to be questionable. Is that a sine wave or is it something else? And if you now even continue, 8, 9, it's just get messy. You will have no system in it because we don't have points enough to describe it. So yes, it is definitely limited depending on the number of points, how the highest frequency, you might say, that you can represent. So don't overdo it here, definitely. Yeah, so the smallest wavelength will be then 2 times your delta x. And even smaller than that makes no sense. To speak the language of Multigrid, then we are talking smooth modes and oscillatory modes. Smooth, that's the low frequent anode, which then takes forever to get rid of with these classical methods. The high frequent, we call it oscillatory modes. They can easily be reduced with a couple of iterations with these Jacobi Gauss-Seidel methods. how to find the value of an efficient omega. Again, I would say as engineers, you just play around with it. Omega 1, omega 0.9, 0.8, you play around with it and see which one is most efficient. Here they have done a little bit of calculation trying to find a very good omega. It's not an over-relaxation anymore, it's an under-relaxation actually. So yes, you can plot the different eigenvalues as a function of different omegas, and here as a function of the wave length, actually the number of points that you have. And for omega equals 1, well, the smallest modes, the smallest waves will then still have a high eigenvalue. What would have been nice here would be to have very small values for these eigenvalues, small as possible, but it should be small for, say, this part of the wave length spectra. For small waves, there he should be efficient to damping down everything. And omega 1 might not be so efficient there. Omega 1/2 looks promising, but he's very promising only for the very high frequency. For the lower frequency or medium frequency, he is not that efficient anymore. So 2/3, omega 2/3, sort of has been chosen as a very good average, covering sort of the interesting part of the frequency spectrum where we want to have the error reduced. But omega 1 works also quite nicely. So it's a little bit discussion here, finding a good omega, and it's possible to show that omega 2/3 is, yes, that's a very good choice. Yeah, I won't go through this one in detail, so have a look at it if you like, but practice we don't need it. Now for visualization, what we have so far, Jacobi, omega is 2/3, and then we have here 64 points altogether. And then we start with different errors, and then we do 1 iteration and we do 10 iterations. So the first one, k equals 3. And to the left, top left, there you now have only 1 iteration. And you can't really tell that he has dropped a little bit. But 1 iteration, he's a little bit smaller than 1 up here. After 10 iteration, this is what you get. So the error has hardly been reduced at all. Waste of time. Here, high frequent. Only 1 iteration for the first one. You see the error has dropped from the initial value of 1. It's dropped quite a lot. And after 10 iterations, well, he's fairly close to 0. Very efficient. And here you now have the combination, superposition of those two. You have 1 low frequent and 1 high frequent superimposed, and you see the effect after 10 iteration and also after 1 iteration. So the high frequent modes will disappear quite fast. The low frequent, he will stay. And yes, you can still look at spectral radius for this one as well, but don't worry too much about these plots. So the properties, convergence properties for these relaxation schemes, the classical iterative schemes, Jacobi, Gauss-Seidel, they work very well for the first couple of iterations. If you have high frequent errors, then they will be removed very efficiently. But the low frequent, it's very, very bad. And this property that they are clever to filtering out high frequent noise, That is what we are searching for, a smoothing, good smoothing property. That's what we like. Okay, any questions so far? Then we take a break.